Thank you very much. It's really an honor to be here today, and I hope here that what we're trying to do is, in about 30 brief minutes, give you an idea of how we designed the tower. First, the superstructure and some background, and then Alan will talk a little bit about the geotechnical issues and the foundations, and then we'll end up with some construction slides showing where we're at today. So. Just a little bit to get started with here. Besides Alan and my firm, who are designed structural engineering and geotechnical, Adrian Smith and Gordon Gill Architecture in Chicago are the design architects. And Adrian and Gordon are two old colleagues of mine. They were also at SOM for many years, Adrian much longer than me. But we've been working together on projects for over 30 years. This project we've been working on for over 6 years. And it's one of those projects that takes an awful long time to germinate. And it's a sort of a once-in-a-lifetime kind of project that way. After a few fits and starts, we finished the design documents in August of 2013. And as all things in the Middle East, basically all the design is to US codes, and this project is no different. The reinforced concrete design is all to ACI 318. Just to give you a little bit of where we're at in the world, Jeddah is on the Red Sea. It's on the western coast of the Arabian Peninsula. And Jeddah is the gateway to the two holy cities of Mecca and Medina. So all the pilgrims that go to Hajj, they come through Jeddah and come through the airport there. And that's, so it's a major hub and a major sea hub. The project is being funded by a consortium of 4 entities, of which one of them is the contractor, the Saudi Bin Laden Group, and another is the Kingdom Holding Company. And the chairman of Kingdom Holdings is Prince Al Walid, you see there. He visited the site during the piling construction. And I think many of you have probably seen Prince Al Walid on CNN and other news programs. He's what they call the Saudi Warren Buffett. He's the one that has a controlling share of Citibank stock, for example. But he visited the site there, and if you look really closely, you see the engineering drawings for the pile foundation that Alan and I authored. So the tower will be sort of the linchpin for a very large master plan of Kingdom City just to the north of the airport in Jeddah. And it's now, other than the tower itself, a huge vacant lot. But you can see what's going to happen there. The tower is going to be surrounded by several other tall buildings. Some of those are 60, 70-story buildings. And the idea is to build the tower first, and then it'll attract a lot of people that want to live in the shadow of the tower, schools and other. It'll be basically a city within a city by the time it's done. The plan is well over 10 years down the road by the time the entire master plan is completed. Here's the current lineup of tall buildings, just to get you organized here. The second tower there is the Burj Khalifa, the current tallest building at 838 meters in Dubai. The third tower there is Shanghai Tower. That's a Thornton Tomasetti project that just topped out recently in Shanghai, 630 meters. Tallest building in North America is the new One World Trade Center. You see Taipei 101 there, which was another TT building that was tallest building in the world when it was completed. And not to be outdone, of course, is the venerable Sears Tower. It actually looks taller than the One World Trade Center, Alan, but we won't get into that. So, the tower it's a mixed-use tower, but primarily residential. Down at the bottom of the tower is a few office floors. There'll be a 5-story hotel, service apartments, and then primarily residential condominiums, primarily. It's tapered there, so you can kind of get an idea of how the floor plates tend to get smaller and smaller as the tower rises. And then you get into what they call executive suites. So those are offices, but they're not highly populated offices. They're very exclusive. And then the penthouse and the observatory deck is dedicated for Prince Al-Walid. He's already purchased that. And then the Spire does not have any occupancy whatsoever. In terms of the structural systems, it's really two systems that are very similar that are joined at the 2/3 height. And I mentioned before the top of the building is unoccupied. They're both a form of bearing wall. So the bottom one there it's basically walls and up to 670 meters. And then there's a transition piece, and then there's the Spire. There's no discontinuity between the two systems. It's a very continuous system, but it's a bearing wall system. It's not only going to be the tallest building in the world, it's going to be one of the most slender. And we measure slenderness by the height of the tower divided by the least dimension at the base. And that number for Kingdom Tower will be about 12-1. Just to give you a point of reference, Sears Tower is closer to 7.5-1. So the buildings are getting more and more slender, and of course more and more tall. A little history lesson. The bearing wall system has been around a long time. The Burj Khalifa, there's a lot of similarities between Kingdom Tower and the Burj Khalifa, but there's some differences too. But the bearing wall system goes back many decades. It's a tried and true system. If you really wanted a building that looks and has a system very similar to Kingdom Tower, you'd go all the way back to the early 1970s with the Sinn Tower in Toronto. Both buildings taper. They're both reinforced concrete towers. They're both organized with three legs that taper. A lot of the structure is at the ends of the three wings, which is a little bit dissimilar to Burj Khalifa. And so nothing's 100% new. So 45 years ago, there was a little Kingdom Tower built up in Toronto. This is sort of an isometric. Gives you an idea of the structural system in a nutshell. It's basically all walls. There's not a piece of wall that's not connected to another. They're all connected by coupling beams. So everything participates in resisting gravity and lateral loads for the tower. There's no columns. Now, my colleagues always get a kick out of that when I say there's no columns. How can there be no columns? Because there's all walls. There's no outriggers. Almost all super tall buildings now have outriggers. There's no outriggers in Kingdom Tower. There's no column or wall transfers, very common in tall buildings. All the floors are flat plate floors, reinforced concrete flat plates, without any spandrel beam whatsoever. The system is as simple as we can make it. I would call it Burj Khalifa taken to its logical conclusion, is the best way of thinking about it. In terms of planning, what happens is at the lobby at the base of the tower, you get into your elevator in the central triangular part of the core there. And then you go to your, either to a sky lobby and get into another elevator, or you go directly to your residential floor. And then you go down a long corridor in one of the three wings, and on either side of that corridor, we've arranged structural walls. And then you turn left or right through a door into your unit. And above that door, of course, is a very important coupling beam in the system. And then at the end of each wing is the fire escape stairs. And those are the new rules to having the fire escape stairs as separated as possible. So this is a very important safety part of the project. And it's where we've organized a lot of the structural walls at the ends of the three wings where they can do the most good. The form of the building in terms of its geometry is the three wings tilt at a constant angle. So basically the three wings are equal in length at the base of the building, and they tilt at or incline at a single angle, but the three wings have slightly different angles. So therefore the three wings hit the top of the tower at three different elevations. There's wing A is the tallest wing C is the second tallest, and wing B is the third tallest. So it's as simple as that. There's no kinks or discontinuities or breaks in the wings whatsoever. The geometry is as simple as we can make it so it could be built. Here's the transition between basically the two bearing wall systems. They come up to about 670 meters, and then the floor plates are too small and there's no program above that space, so we have a transition piece. What happens is the three end walls at the ends of the three wings get very, very close to each other, but they not quite touch each other. But they continue up and form 3 of the walls of the spire. So that's the continuity of the 2 systems. And then there's several other walls in between that get transferred on what we call a 4-meter thick SkyRaft. So it's 670 meters over 2,000 feet in the air. That's what the transition is. Here's what happens in the residential units. Basically, you have walls in some of the units, but you can see the kitchens and the bedrooms and so forth are arranged around them. The system works really the best for residential. It doesn't work well for open plan office. So it's tailored for these types of residential buildings. There's a hierarchy in the walls. Starting from the beginning, in the middle, the triangular core creates a lot of the torsional stiffness of the building. This is very important for the performance of the building in the wind. There's very few openings through the triangular core, and that's 800 millimeters thick at the base. And then connected to the triangular core are the corridor walls and the stair walls. Those are highly stressed, and they're the ones that have the most openings through them. Those are 1,001 meter thick at the base, and they get pretty heavy reinforcement at the base of the tower. The cross walls, I would call them more stabilizers. They're very important to the stability of the tower, but they're the thinnest. They're 850 millimeters at the base, relatively lightly reinforced. They have coupling beams that continue all the way across the corridor. So there's 3 span coupling beams connecting all the fin walls across the corridors. And of course the end walls. Those are the inclined walls along with the stair walls. Everything else is vertical. The walls, only walls that are inclined are the end walls and the stair walls, and they get to be 1.2 meters. So that's the thickest wall in the entire tower, 1.2 meters thick. There's much taller walls around the world on buildings that are less than half the height of Kingdom Tower. Materials, high strength of course, but nothing exotic. For concrete, we're specifying up to 85 megapascal concrete at the base. That's about a little over 12,000 PSI concrete. Again, high strength, but not unusual. I would have liked to have had a little bit higher concrete, but Saudi bin Laden Group, the contractors, limited us to that in terms of their quality control. We're using a little 75 KSI rebar, but by and large, all of the reinforcing is 60 KSI. And because the reinforcement gets a little bit heavy at the base, almost all the lap splices, we're not using lap splices at all, we're using couplers for all the vertical bars in the walls to reduce congestion and to get construction moving quicker. The seismicity is, I would call it low to moderate. Basically the Arabian plate is stable. There's very little seismic activity, but there's a little bit of activity up by Sinai, but other than that, most of the activity is up around Iran and Turkey. So on these tall buildings and almost all the super tall buildings, it gets down to wind. And we've done, as you might imagine, many, many different wind tunnel tests. We start with a very quick model, 1 to 800 scale force balance model, as soon as we won the competition. And then we moved into more complicated pressure integration models at 1 to 600 scale. This is the limit. That's the biggest model that you can put in a wind tunnel, actually. And those models have pressure taps over the entire surface. So you get all the local pressures, and then you integrate those to give the structural loads and responses. And because of the pressure taps, they couldn't get enough wires up into the top. They had to do a half model for the spire only, and that was at 1 to 400 scale. And finally, we did the aeroelastic test. All these other tests are rigid models, but the aeroelastic test is the one that actually models the damping and the stiffness of the tower itself. So you get the feedback effects between the tower and the wind. And some of these towers that we've done, not many, we actually do a separate test in a wholly different wind tunnel. So most of the wind tunnel is up at RWDI laboratories in Ontario, Canada. But we did one test at the exact same scale with the same testing technique, and we gave them the same properties to another wind tunnel, the Boundary Layer Wind Tunnel Laboratory at the University of Western Ontario. And we told them, don't talk to each other. So we had them test the 2 towers, and then we compared the results, and the results were really quite close. So that was very comforting in terms of, because these are pretty small scale models when you think about it, 1 to 600, 1 to 800 scale. We measure the performance in terms of the motion that the occupants of the tower are predicted to feel. And we use the ISO 10137 criteria at 1 year. So the criteria you can see there, you would be allowed 12 milligis at the highest occupied floor, which is 655 meters above grade. And the predicted accelerations from the wind tunnel test are less than half of that. It really should be a very, very comfortable building without any auxiliary damping for the occupants. And the reason why that is, it's concrete. I don't think, sorry if there's any AISC people here. The tower would not be able to be done in steel, I'm afraid, but the mass is important, the tapering is important, and the 3 legs are important. So those are the three most important drivers. We do many different types of models, CSI products, Midas Gen, Strand, Abacus. We do them at different times. We do use different engineers. So this is a way of checking us. So we start at the beginning of the project. When we move to another phase, we'll use a different type of model and probably a new engineer and keep checking against ourselves. The natural period of the tower is about 12 seconds, first 2 modes, and the third mode, torsional, is about 6 seconds. We think that's very stiff for such a massive tower. For the vertical shortening analysis and the stage construction, we use Midas Gen, which is a Korean program. We use it as sort of an engine, and we put the material properties into that, and we couple that with the construction schedule that we get from the contractor. This is all done in 3-dimensional models nowadays instead of Excel spreadsheets. This is the mixed design for the 85 megapascal concrete. The material properties for the creep and shrinkage of the concrete are actually being tested outside of Chicago at CTL laboratories. There's no laboratory in the Middle East that can do this testing. You can see the creep frames there. And this testing, they basically shipped all the constituent materials for the mix to Chicago, and they batched the samples there, and they're testing and have been testing for over 1.5 years now. One last thing before I'll let Alan take over here. When you think about it, tall building structures are one of the few man-made products that aren't really verified at full scale. It's not like an automobile or an airplane where you can do scale model testing. You basically start with a finite element model, which is an idealization of the structure. Then you do wind tunnel testing, as I mentioned, at 1 to 600 or 1 to 800 scale. And then you build these towers, and there's precious little feedback between how the analysis assumptions and the wind tunnel testing really is borne out by the facts of how the tower behaves over its lifespan. So we have put together a long-term structural health monitoring for the tower that's going to be instrumented from the bottom of the piles all the way to the tip of the spire. The owner and the contractor are on board for this. It's expensive, but we hope down the road, well after I'm retired, of course, we'll be getting some good data from the tower that can start to inform how we're doing with our analysis and our basic assumptions for these tall towers. So with that, I'll ask Alan to come up and give you a little bit of background on the geotechnics.
Great, thanks, Bob. So I guess it's up to me to take it home for the conference, and I'm going to focus on really the spirit of the conference, which is the structural interaction with the foundations. So just some foundation, stats for the foundation. We foundation guys like, that good performance of the structure we pay for in load. So we've got a massively loaded building, 860,000 tons. It's about almost double what Burj Khalifa is. That realizes to a average area pressure of 2.65 MPa, or almost 30 tons per square foot, over a 3,200 square meter tower raft base. So this thing is massive. And we've got about a distance of about 60 meters from center to edge. The raft itself ranged from 4.5 meters to 5 meters thick. The foundations are 270 piles, bored concrete piles, ranging from actually two different 1.5 meter diameter and 1.8 meter diameter at about 2.5 D on center. And an average service load, if you just take the load takedown and put it all on the piles, of about 32 meganewtons. And I remember when we first started, Bob said, yeah, let's go for a differential settlement of 25 millimeters from center to edge. And it's like, all right, we'll see what we can do about that. So boring location plan, obviously did a number of borings, typically 100 to 200 meters in depth. And this is just an idealized profile. I've got a thin layer of fill on top, only a couple of meters. And then we got into a Coralline limestone. Below that, that sort of tapered into a mudstone. And then there was a distinct gravel layer at about 50 meters depth. And then we got into a poorly constituted sandstone down to about 100 meters, then a thin conglomerate layer, and then a much more competent sandstone at about 115 meters. And you can see that in the UCSs and the E-modulus values. And really what this told us is, hey, ground does sometimes get, rock gets worse with depth. It doesn't always get better with depth. We really saw that also with some of the geophysical testing. The shear wave velocities really dropped in that zone. So it really, it was real. The limestone itself, RQDs were typically greater than 50%. And then we got into that poorly constituted sandstone, and sometimes we were driving split spoons. So just some pictures. This is the limestone. You can see, it started out as a coral reef, almost undoubtedly, and then morphed into a limestone. It's got a specific gravity of about 1.8, so it's like medium dense sand. And it sort of plots on the soft to very soft range if you look at the if you look at the Don Deere plot. The mudstone and gravel, just wanted to highlight the gravel zone itself. Again, this was at about 50 meters, subangular. We actually pulled out some, it looked like mountain river rock out of some of the spoils of the piles. So this was really influenced our thinking in the beginning about how deep we wanted to take the piles. Just imagine trying to bore piles through those, could turn into marbles. So then we went and just did rough geotechnical capacities. Ultimate bearing capacity, we figured it was pretty close to the UCS of the limestone, so about 2.5 MPa, take a factor of safety of 3, and we're at about 800 kPa allowable bearing, obviously much less than the average bearing pressure of the tower. Single pile capacity, 1.5 meter diameter, 45 meter long, taken to various methods, but we figured about 450 to 500 kPa as an ultimate and penciled out to about 42 meganewtons. We took the 45 meter long as a design length because a couple of reasons. We wanted to stay above the gravel, so we did that. And then also with the limestone, it's obviously a soluble rock. We did not find any major cavities in all the investigation that we performed, but we figured, hey, if there's anything down there, we will fill those cavities in or any voids in with the concrete just in constructing the piles. So that was kind of the thinking behind the length of the pile. So we're going to then go to full-scale field load test. The owner was willing to engage in this well before well ahead of completion of the design. I'm a University of Illinois guy, so you have to do a footing load test like we did Don Deere did at the World Trade Center 50 years ago. So it's a 1.5 meter square block of concrete, and then we also performed O-cell tests, 2-tier O-cell tests on both board piles and circular piles and rectangular barrette elements. So just a general, so this is the result of the footing load test. At about 8 meganewtons, we had about 10 millimeters of settlement, mobilized a bearing pressure of about 3.3 MPa, and back calculated a modulus of about 550 to 600 MPa, sorry, 550 to 600 MPa. And then this is just one example from the load tests, just highlighted a drill line there at an ultimate side shear of 500 kPa. Immobilized, in some cases, much higher than that. The one on the top is almost 2,500 kPa, which is getting close to the average UCS of the rock. So I think at that point, you're failing it through the rock as opposed to the rock-concrete interface. So then with all those tools, we go into and do our, engage into our more detailed finite element analysis and design. So this is a load takedown, just first cut from Bob and his team. And we carved it into this middle section and then 3 wing sections. They're basically equal areas there. So you can see the 3 wings are essentially it's very similarly loaded, plus or minus 5%, and a little bit heavier in the center. But overall, it's a very uniformly loaded building. I mean, this is not a center core, massive, heavy center core and perimeter columns. As Bob described, it's got walls all the way out to the end, and it's loaded that way. Just no equations in this. I know you're all beleaguered from equations from the conference, but just some concepts, right? So on the right-hand side is you know, the classic beam on elastic foundation type diagram. So flexible foundation, you know, will have a very non-uniform settlement profile, but it will have a very uniform pressure profile. And conversely, a rigid foundation will have, it's rigid, right? So it's going to settle the same, so have uniform settlement, but it will have a very non-uniform pressure distribution. And of course, on the left-hand side, you know, Winkler springs, you know, some thought, hey, if the loads are coming down, all the piles are the same, the individual pile springs should be the same, they'll be loaded the same, and the settlement will be the same. But it doesn't always work that way. So just a bit about, this is the iterative process and the collaborative process, right? So this is sort of Langan's and TT's approach to this project and frankly other projects as well. And I've heard sort of the common themes from some of the presentations I saw at the Congress. So column loads come from, obviously, from structural engineer, and they could be a fixed base analysis, or in this case, it was uniform springs on the piles and a load takedown. We take those loads and we apply those to our model. And determine settlements, determine piles, loads on the pile, and also bearing pressures under the raft. Calculate springs, both for the piles and for the subgrade modulus. Give those back to Bob and his team. They'll run it through, I think they were using E-tabs at this point, run it through, and in some cases, the wall loads will change. So we take those new wall loads and put it back into our model and get a new settlement profile, et cetera. So we go back and forth like that. We like to think that we want to converge on wall loads. We want to see the wall loads not moving around more than a couple of %. And we want to converge on settlements and also pile loads to, I would say, typically within 10%. On this project, we were within 5%. That was sort of because of the importance of the project, we held ourselves to a bit higher standard. So this is our finite element model, the idealized profile. We model the ground, obviously, the piles as embedded beams, and the raft as a plate with its appropriate thickness and stiffness. And then apply, as I said, the loads that Bob's team gave to us on the top of the raft. So this is the first cut. This is the first one we did, 45-meter long piles uniformly throughout. And we had essentially 175 millimeters at the center, 100 meters, 110 millimeters at the edge. We had an angular rotation of about 1 on 900. And we thought, hey, we're doing pretty good, right? I mean, we're double, 1/2 of 1 on 500, which is sort of the rule of thumb concrete structure, right? And we thought we were doing pretty good. So we started iterating. Ours are on the top. TT's safe model is on the bottom. And you can see that we're not iterating. We're not getting close to convergence. And in fact, on TT's model, we're starting to see reverse curvature on some of the wings. So we kind of took a step back, changed our perspective, and said, wait a minute, what's going on here? We plotted pile loads. So on this one on the left, the 0, 0 is the center line of the tower, and then 60 is out at one of the wings. And all those dots are pile loads and pressures as well. And instead of having a uniform load from center to edge, we had much higher pile loads at the edges and much lower loads at the center. So this thing is behaving like a classic rigid foundation with uniform, trying to get uniform settlement, but having a very non-uniform distribution of the loads. So we said, all right, well, that's not working either. And I remember Bob at one point saying, wait a minute, the raft can't even handle the raft. There's no way the loads could come down and the raft can transfer it out. It's not going to happen. Well, when they started looking at their model, it wasn't happening at the raft level. It was happening probably 20, 25 stories up in the building. So at that point, the load was starting to walk out to the end walls, and we were seeing, we had not finished converging yet, and we had, the wall loads were increased by a factor of 2.5, 2.25, almost 2.5. And as Bob said, it was kind of turning into the Eiffel Tower effect, right? So all the load was coming down in the middle, but it was ending up on the edges. And that was causing a lot of problems for us, for everybody. If we were trying to design for that, walls would have had to get much thicker, so nice apartment layouts would have suffered. We'd have to try and figure out how to get all the piles over to the, get all the loads to the, into the piles at the wings, and it was just really turning into a disaster. So again, we looked at it from another perspective again and said, all right, well, really what we need to do is control differential settlements and control total settlements of the center of the tower. And we can't stuff any more piles into this thing. It's already 2.5 D on center. So of course the solution was to take the piles in the center of the tower deeper. So they ended up as 105 meters in total length. And we did that we wanted to stay above that competent sandstone at depth. We didn't want to have hard points at the center of the tower. So we chose 10 meters above that to give ourselves a nice cushion. And then we stepped it up at 2 intervals, 85 meters and 65 meters. And then we kept as many piles as we could at 45 meters. We still had this gravel zone that we didn't want to, if we didn't have to penetrate it, we didn't want to. So now things start looking a lot better. So on the left is our first cut again. That's the first wall loads takedown. And instead of 175 at the middle, we've got 107. And the first iteration, the wall loads did move around some still. We had about 50% increase on the end walls, but not nearly as bad as the first cut. And then our second iteration, the wall loads were essentially all less than 10%, and most of the time less than 5% change. So we felt like, all right, we've got it now. And then from that point, we sort of tweaked, we never changed the pile springs. We tweaked area springs. So at the end of the day, the geotechnical model and the safe model matched, and that's this plot here. So again, in plan, these are 100 millimeters at the center for us, 102 for TT. And of course, are we saying that it's going to settle this exactly 100 millimeters? I mean, of course not. But at least what we're saying is it's highly predictable. We both agree on how the foundation is going to behave. The pile loads, similar, within 1 or 2 meganewtons at the most. So again, we're in agreement on how the raft and the foundation is going to perform, and that made us both feel a lot better. So this is bearing pressures. Yellow is what, about 350 kPa, so very uniform. We've got a little bit increase at the edges, which is kind of matched what we saw in the wall loads moving around a little bit. The subgrade does take about 22% of the foundation load, which was useful not so much for geotechnical capacity, but for structural capacity of the piles. We really took advantage of that fact. And then the wall stresses, the similar model, again, wall stresses increased at the end walls by about 60%, but at least it wasn't more than a factor of 2 like we had been seeing before. And as Bob said, we're measuring structural performance of the tower as it's being constructed, and settlement points are being taken on the top of the raft. So this is at about 25% of the total gravity load on the raft. And that's at 10 millimeters at the bottom, not 100. So far we've got about 5 to 6 millimeters of movement for the center of the raft. And wing A is again about 5 to 6 millimeters, and the wings B and C look about the same. I think it's going to take off a little bit as the stress increase at that lower weaker layer, the poorly constituted sandstone starts increasing. I think it's going to increase some, but I think overall we've probably overpredict settlement probably by a factor of 2 is what my guess is. But again, I have Clyde Baker chirping in my ear every time, and he says, when you're doing something that nobody's done before, take baby steps. And tallest building in the world in a place that has no development at all and not really well understood geology, I think I'm okay that the foundation may be a little bit over-designed. So final thoughts, in our view, the geotechnical model governs the ground settlements. The iterative process, not only necessary, but also gives insight into how the column and wall loads are going to move around as you converge. The stiffness of the superstructure and the stiffness of the foundation really have to be compatible, and that's what we saw in the beginning. Our foundation was too flexible, and the structure was really suffering. And in this case, the longer piles are not needed for geotechnical capacity. It's for settlement mitigation. And then the last one I will end with is, Bob, you were right, 25 millimeters from center to the edge is achievable and necessary. So for the geotechs, yeah, listen to your structural engineer. Sometimes they are smarter than you think. So So just some construction shots. I'll do a few and then Bob will do a few. So just a cage going in. Again, saw this one before the O-cell. This is actually the rock was soft enough that basically it could be excavated with a bucket like this with teeth on it. So it was quite easy to excavate, and the limestone really held up nicely just under water slurry. So it was nice. This waterproofing with the cathodic protection. We had cathodic protection on the pile reinforcement as well. And then I'll let Bob take it home.
This is sort of the beginning of the placement of the bottom layers of reinforcing in the raft. And there's only a few layers. Trust me, by the time they were done, the layers were all the way up to the top of those dowels coming out of the pile heads. So there was 15 layers in each direction. But this is one wing. They did a test cube for the raft. This is a 4.5 meter on a side test cube with the mixed design that you see there. So they put thermocouples in there to make sure the heat hydration was under control. They do use ice there a lot, not just for foundation elements, but for tower walls and so forth. So that's very common over there. The mix is basically self-consolidating concrete for the mat foundation. This is what a 5 meter thick mat foundation looks like formed up. Basically, the mat was poured in 4 different pours, the 3 wings, and then the central part was the 4th pour. But that formwork itself is a real construction site. And then the placement of the concrete is all done by placing booms nowadays. And with self-consolidating concrete, there's precious little workers actually where the concrete's being delivered. This is a big advancement in the state of the art for the last 10, 12 years for all different types of major projects using different mix designs and different construction technologies to deliver these high strength concretes. So you can see there. Now you'll see the last pour of the mat there has insulation on it to keep the differential temperatures down. And that pit there in the middle is the elevator pit. For where all the elevators are in the center of the tower. But you begin to see the first walls being constructed there with basically the cross walls and the corridor wall and the stair wall for the first wing. That was very exciting to see those first pictures come from Saudi Arabia. And the walls are being jump formed, and you can kind of get an idea of the system here. They're done with little construction units. And the way these towers are built with the bearing wall system is the slabs all come last. So the walls all go ahead, and the slabs are connected through the walls through couplers and keyways. So it's not a conventional type of construction at all. It's, the walls actually went up 20 or 30 stories before there were any slabs poured whatsoever. But that's the formwork system. And that was taken about a week ago. And we're up at about 150 meters. Alan mentioned that 25% of the concrete in the tower has already been placed, and that's because we have a 5 meter thick raft. All the thicker walls are at the base of the tower, and the walls taper. So they get thinner as you go up, and you have less of them, less slab area. So believe it or not, you would look at it from the picture here, but over a quarter of the concrete is already in place. And you can start to see some of the slabs being placed there. They jump started and went to level 7, and they're going to continue up. I think that by the end of 2016, I'm hopeful that we'll be up at around 300 meters, something like that. And the tower is scheduled for completion now sometime in 2019, and perhaps the structure topped out in 2018, plus or minus. Don't hold me to it. I can only design, I can't build it for them. So, but with that, I'd like to thank you for your attention, and I think that's all we have. Thank you very much.